Hi, my name is Clément Romac, and today I'm going to talk about TeachMyAgent, which is a benchmark for automatic curriculum learning in deep reinforcement learning. This work has been jointly done with Rémi Portelas and Pierre-Yves Oudeye from INRIA France and Cathy Hoffman from Microsoft Research Cambridge. In this talk, we'll first see a bit of background and especially what automatic curriculum learning is. Then we'll see and I'll present TeachMyAgent, which is our benchmark. We'll see the results we obtain with it, and we'll discuss them. Okay, let's start with a bit of background. In past years, part of the deep reinforcement learning community has been interested in no longer learning a single task policy, but rather a policy which can generalize over a set of tasks. To obtain this set of tasks, some works used procedural content generation, which means we have an environment whose generation is encoded with a task space. With such a task space, possibly containing tasks of various difficulty, one may wonder, how can we design an efficient curriculum? So how can we organize the way we present tasks to our deep reinforcement learning students, given that some tasks in the task space may be harder than others? So for this, the field of automatic curriculum learning, or ACL, has been studying this problem. So let's present the background and the framework of automatic curriculum learning. So on the right, you can see a schema of a classic reinforcement learning loop. So you have deep reinforcement learning students, which can act in an environment using an embodiment. So it does actions with the steps in the environment. Then it gets an observation and a reward, and the loop goes on. Here, the environment is generated through a procedural generator. And so with this loop, and given a deep reinforcement learning student S, a task space, which is an n-dimensional continuous space who is encoding the procedural generator. Given any information we can record from the past, so it can be episodic rewards, it can also be observation and rewards of every step. We can have an ACL teacher, which is basically a task selection function, which learns to map the information retained from the past to a distribution over task space. So what it means is that you still have your reinforcement learning loop, which in our case is an episodic setup. And outside of this loop, at every episode, you use your ACL teacher to sample a task vector from your task space and use this task vector to generate your environment for the new episode. And then at the end of the episode, you gather information, you update your task selection function of your ACL method, and you keep generating environments. So what we want from an ACL teacher is, given a budget of E episodes, we want it to maximize some performance metric P over a distribution of test tasks. Okay, so here's an overview of state-of-the-art ACL methods in the case where we are, so episodic setup with a continuous task space. So first, there's ALPGMM, which was introduced by Portelas et al. In 2019, which is a method that tries to maximize learning progress over training. In the paper, they compare ALPGMM against CoVAR-GMM and or IAC, which are two other methods. We can also talk about Golgan, which is a bit different. It uses a neural network to generate goals, and in that paper they compare their method against RAIC. There's also Setter Solver, who's also using neural networks to generate tasks, goals, and they compare only their method against Golgan. And finally, there are methods that have a task distribution and they make it drift over the task space given the student's capabilities. So for instance, there is automatic domain randomization, or ADR, which was introduced in OpenAI et al. 2019 with no comparison against other ACR methods. And there's also self-paced deep reinforcement learning, or SPDL, which was compared against ARPGMM and Golgan. So what we can observe here is that we do not have a thorough comparison of all the methods, each comparing itself against some others. And in each of these comparisons, they all use different environments with different characteristics. So there's no systematic comparison between methods. And moreover, there are some of them that are not open source released, so you cannot use them. Then, in addition of the different setups and environments they used, some of them are also using or even requiring what we call expert knowledge here. So you still have your reinforcement learning loop, which does not change, and your student always has access to the observation and the reward at every step. But in some ACR methods, we can or we need to give to the method some prior knowledge beforehand, simply to help it designing the curriculum. So among the methods we've introduced before, we identified three kinds of expert knowledge. So the first one is what we call initial task distribution. So basically, some methods use an initial task distribution that you give before training, and you usually want to set it somewhere in the task space where tasks are easy. So the teacher will start generating tasks in this region of the task space. Then similarly, you also have target task distribution. So for the initial task distribution, you say where the teacher has to start sampling tasks at the beginning of the training. Well, for the target task distribution, you simply say where you want the teacher to end up sampling tasks. So you usually want to set this to a subspace of the task space which contains quite hard tasks. And finally, we have what we call reward mastery range. So it's basically some function that teacher can use to identify what a master task is given the reward. So for instance, we have Golgan and Setter Solver that do not use the dense reward of the environment, but they rather use a binary reward with 1 meaning success and 0 failure. So we want a function that maps the dense reward into a binary one. And for ADR, they use thresholds where we want the reward obtained by the student to lie in. So these are also expert knowledge you need to bring, because you need to know what reward you can obtain in the environment and what a good reward means. So in our paper, we provide this table which lists all the expert knowledge you can use in the state-of-the-art methods and whether it's required or optional. So given this, and given the variety of setups and environments we've seen before, we can say that some comparisons between methods are quite unfair because there are methods using expert knowledge which compare themselves against methods that do not use expert knowledge. And so again, there's no systematic comparison of ACL methods. Before going into such a comparison, we took a step back and tried to identify what are the key challenges, the key teaching challenges we want an ACL method to do. And so we've identified 6 key challenges. First, we want ACL methods to be able to deal with task spaces where most tasks are infeasible. So in such a case, you want your ACL method to be able to find niches where your deep reinforcement learning student can actually learn, so when tasks are feasible. On the opposite, you also want your ACL teacher to be able to deal with mostly trivial task spaces, because in these task spaces, most of the tasks are trivial, so you could simply sample them randomly, but you may have some niches with a high learning progress, so some niches where you can actually learn interesting skills, so you want your ACL method to be able to find them. Third challenge is, we know that deep reinforcement learning can suffer from catastrophic forgetting, and so we want our ACL teacher to be able to track it, to see whether our student has forgotten some skill it has learned before, and be able to go back to this task and make it learn the skill again. We also want the ACL teacher to be robust to diverse students. So it means diverse deep reinforcement learning methods, but also diverse embodiments in diverse environments. 5, we want it to be able to deal with rugged difficulty landscapes. So what this means is that we want our ACL method to be able to find the curriculum where the optimal curriculum is not a smooth drift inside the task space, but rather jumps in some subspaces, because there are subspaces of high difficulty in the middle of the task space. And finally, we want it to be able to deal with no or little expert knowledge. So basically what we would like is an ACL method that can work well without any expert knowledge, and maybe work even better with some expert knowledge. So given the lack of a systematic comparison in ACL methods, and given the challenges we identified, we wanted to propose a systematic platform benchmark and comparison of methods that would rely on these challenges and compare methods in each of these challenges. So we introduced TeachMyAgent, the first version. So basically, TeachMyAgent is a benchmark platform for ACL methods. You can see a schema showing all the parts of TeachMyAgent on the right. So we provide multiple deep reinforcement learning students, multiple embodiments, multiple environments. Then we implemented state-of-the-art ACL methods. And given all of this, we propose 2 kinds of experiments to benchmark methods. First, skill-specific comparison, so on each of the challenges. So we can compare ACL methods on each of the 6 key challenges. And we also provide a global performance assessment experiment to like compare the methods. Okay, so now let's give a look at each of these parts. So first, we re-implemented all the ACL methods we saw before. So most of them were taken from open source releases. We just had to adapt them for our common API. But some others like ADR or Setter Solver weren't open source released, so we had to implement them following the white papers. And so all our methods are using a common API, so it's fairly simple to add a new method. We tune the hyperparameters of each method using a grid search. So we used approximately 70 points for each method in a 7 million steps training setup with 16 seeds. We provide all the setups in our appendices. And so we chose the range of each hyperparameter given the white papers. Then for the deep reinforcement learning students, we used 2 different students. So we used soft actor critique, which is an off-policy method, and we took the implementation from OpenAI spinning up. We also use proximal policy optimization, which is this time a non-policy method, and took the implementation from OpenAI baselines. We slightly modified them to fit our API. So in our API, we still have the vanilla reinforcement learning loop, but we have to include the ACL teacher to ask it to generate the environment at every episode, and also to record and store information to update its sampling policy. We also tune the hyperparameters of each of our deep reinforcement learning students with a grid search. Then we provide 2 environments. So the first one, which we call the STEM tracks, was taken from Portelas et al. 2019, which is the paper that introduced ARPGMM. And this is an extension of the bipedal walker from OpenAI Gym. So this is a very simple task space with 2 dimensions. So you basically control the height of the stems and the spacing between 2 stems. The environment, the generation is stochastic. And so you have a walker that has to, we want it to reach the end of the map. And so to do this, we just reward the agent for moving forward. Then we extended this very simple environment into a much more complicated one. So we call it the parkour. So you can see it has a ground, a ceiling, but also some physics. So first, the ground and ceiling are generated using a compositional pattern producing network, so a CPPN. The idea is that you provide a 3-dimensional vector as input of the CPPN, and then you get the ground and the ceiling. So it's kind of a black box generation of the terrain. With this, it gets much harder to provide expert knowledge, because we actually don't really know what to provide as input, as a vector input of the CPPN to get a very smooth and quite flat terrain. Then we also added water, which is controlled by a single dimension, controlling the level of the water. And we implemented very simple rules to simulate physics in water. We also added creepers so that climbers, you'll see afterwards, can use to learn to climb. So it's controlled by 2 dimensions. First one, like stumps, is controlling the height, and the other one is controlling the spacing. So overall, it's a 6-dimensional task space. So 3 dimensions for the terrain, 1 dimension for the water, and 2 dimensions for the creepers. So we have this environment with different physics, and you'll see multiple embodiments. So it gets quite hard to give expert knowledge, and also because of the new physics and the embodiments you'll see after, given the embodiment you chose in the parcours, you need to draw a different curriculum. So we have in the parcours multiple curricula possible given the student. One thing about the CPPN and why we used it is to obtain, as I told before, a black box task space where it gets hard to provide expert knowledge, and also we wanted the parcours to have most of the challenges we want. So the 6 challenges, we wanted the parcours to have most of them, to have like a complicated environment where you could evaluate future ACL methods. So first, what you can see is that if you provide a 0 input vector in the CPPN, you'll get the plot you see on the top, so this is the ground you'll get, and the ground isn't flat at all, so we don't know where we have to be in the task space, so in the 3-dimensional vector, to get a very flat and smooth terrain. We'll still get local similarity, so what it means is that if you sample very close points in the task space, you get very similar tasks. And finally, we'll have the rugged difficulty landscape case here. What it means is that you can, if you move only on one of the dimensions of the task space, you can see that in the middle there may be tasks which are way harder than others. So if you want to move along this dimension with your ACL teacher, it must jump and do not simply drift smoothly. Okay, and finally, we introduced some multiple embodiments. We took the walkers from Portelas et al. We also introduced the spider, the walking chimpanzee. We introduced climbers. So basically, walkers cannot touch the ceiling and can live only above water. So after a certain number of steps, of consecutive steps underwater, they die. Climbers cannot touch the ground, so they have to climb on the ceiling. They can use the creepers, and they can't live underwater. So as walkers, after a certain number of steps, of consecutive steps underwater, they die. And on the opposite, we have swimmers, so they can only live underwater, so after consecutive steps above water, they die, and they can touch ground and ceiling. So what we can see here is that we need very different curricula given the embodiment chosen. Basically, for walkers, we would like the ACL teacher to first sample task in the parcours with only flat ground, no water, and then progressively make the ground harder. For climbers, we want flat ceiling and progressively harder ceiling without water. And for swimmers, we do not really care about ceiling and ground, and we want water. Okay, so given all of this, given the set of environments, the set of embodiments, the deep reinforcement learning students, and our ACR methods, we created two types of experiments. So a first one, which is to compare methods on each of the key challenges, and the second one we'll see after, which evaluates a global performance. So first, for the skill-specific evaluation and comparison, we use the STEM tracks, which is a quite simple environment, and we modified its initial task space. So the initial bounds in which you can sample the height of stems and the spacing of the stems. So we modified this two-dimensional task space to create 5 variants. So in the first one, to match the mostly unfeasible task space challenge, we simply increased the maximum height of stems. So you get most, if you sample uniformly random inside it, you get most of the stems which are too high for the worker to go over. So most of the tasks are infeasible. Similarly, for the mostly trivial task space, we decreased the lower bound of the stems height. So you can now sample negative stems height. So most of the tasks contain very small or no stems. For the forgetting students, we simply reset the deep reinforcement learning model. So what we do is that we reinitialize the weights of the networks, and we empty the replay buffer twice during training. For the diverse students' robustness, we simply use multiple embodiments, multiple deep reinforcement learning students. So we do multiple trainings, and we average the results over all of these. And finally, for the rugged difficulty landscape, what we do is that we apply a random transformation on the task space. So the ACL teacher keeps on sampling in an initial task space, and then we apply transformation, and so map the point it has sampled in the initial task space in a new task space. So what we really do is, you can find details in our appendices, but we kind of bin the task space and shuffle the bins. So it creates subspaces in the middle of the task space that have a very high difficulty. So we move subspaces that would have been like on the edge of the space in the middle of the space. Okay, so these are the 5 variants. For each variant, we use 32 seeds. So we repeat 32 times the training, and each time with a different random seed. We do 20 million steps training, and we use the same test set for each variant. So the test set is simply 100 tasks sampled over the original task space of the STEM tracks, and they are evenly distributed over the task space. So what we are looking for here is for generalization. So we evaluate our ACR methods over on a test set which is drawn over the whole task space. So what we really want for our ACR method here is to make the deep reinforcement learning student perform well over the whole task space. So we are seeking generalization. Okay, so we there's one final key challenges we have to evaluate, which is the expert knowledge one and the robustness to few or no expert knowledge. So what we did is basically we created 3 expert knowledge setups. So in the first one, we provide no expert knowledge at all. So we managed to make run some methods with expert knowledge that doesn't help at all. And for the methods that really required the expert knowledge, where we couldn't provide no expert knowledge at all, we simply could not make them run in this setup. So that's the case for GoldGAN, ADR, and Setter Solver. Then the second setup is the low expert knowledge. So we only provide reward mastery range. So we consider this as low because you do not have any assumption on where the simple tasks are in the task space. And finally, we have the high expert knowledge setup where we provide all expert knowledge. So what you have to remember here is that all of these do not change the deep reinforcement learning training. So you still have the loop with the deep reinforcement learning method, doing actions in the environment and getting the observation and the reward. The only thing that this changes is that at every episode, when you want your ACL teacher to generate the next episode, so the next environment, it can access or not expert knowledge. And so what we did is that for each of our 5 variants, we made them, so we ran the training in each of the 3 expert knowledge setups. Okay, and so last experiment we did is the global performance experiment. So again, here we wanted to have like this complex setup to really assess how good our methods are. So we do not really want now to compare them in each of the key challenges, but rather on a very hard task, on a very hard learning problem. So what we did is that we used the parkour, where obviously we could not provide any expert knowledge because we don't know where simple or hard tasks are in the task space, so we could not provide any distribution. And we also, in addition of having the parkour, we made again 20 million steps training, but with 48 seeds. And among the 48 seeds, we have 16 seeds with the walker, 16 seeds with our fish embodiment, and 16 seeds with our climber. And the ACL teacher does not know what embodiment the current training is using. You can note that for each of the embodiment, we created a hand-designed test set to assess the performance. So the test set is different whether you're using a walker, a fish, or a climber. All right, so given all of this, we were able to perform a large-scale benchmark of state-of-the-art ACR methods, both in the skill-specific evaluation and in the global performance assessment. So let's first take a look at the skill-specific analysis. So again, you have all the details in our paper, but here we have these 3 radar charts. So each chart is a different expert knowledge setup. So you have no expert knowledge on the top, low expert knowledge on the bottom left, and high expert knowledge on the bottom right. Then for each radar chart, you have 5 dimensions, which are the 5 challenges we evaluate. So mostly trivial task space, mostly infeasible, variety of students, rugged difficulty landscape, and students that forget. And on each of these 5 challenges for each expert knowledge setup, you have the performance of of each ACL methods. So you can see that on the no expert knowledge setup, you do not see Golgan, ADR, and setter solver because we simply could not run them. And so the performance of each ACL method is shown as a ratio of the performance of our baseline. So we have this random baseline, which is simply sampling tasks uniformly random over the task space. So remember again here, it's on the stem tracks. So we have this 2-dimensional task space. And so yeah, the performance of each method is shown as a ratio of random. We also made statistical tests to track significant difference. You can see which method perform significantly better than random with the stars you can see below the labels. And we also provided an upper bound of the performance achievable on each dimension with the red plus. Again, you can read the paper to see how we calculated this upper bound. Among the things we can see in these comparisons, first, we can see that expert knowledge free methods, which are basically ALP-GMM, Covart-GMM, and or IAC, are quite efficient, even when compared to methods that have access to expert knowledge. Then we can see that the methods that use or require expert knowledge are very dependent on it. So what it means is that when you give them very low expert knowledge, they do not perform well. So you can see, for instance, here Golgan, which is in blue. So Golgan is performing well quite low in the low expert knowledge setup, but in the high expert knowledge setup, it becomes one of the best teachers. In the appendices of our paper, we provide case studies where we look at very specific results we observed. But yeah, one of them is that ADR is unable to solve rug difficulty landscapes. This problem is simply by construction. The way ADR works makes the assumption that the difficulty is not rugged over the task space. So we can see that even with very high expert knowledge, ADR performs very, very poorly on the rug difficulty landscape challenge. Then, okay, so Golgan, as I said, may be one of the best teachers when you give it enough expert knowledge. But there's still this challenge, which is the students that forget, where it performs very poorly, even with high expert knowledge. Again, we study this in our case studies, in our appendices, but this is also due to the way Golgan works. And finally, we can see that self-paced or SPDL is performing very poorly on all of the setups. The reason for this is that SPDL is made not to obtain a student that can generalize well over the whole task space, which is what we are evaluating here, but rather a deep reinforcement learning student that can perform very well in a specific subspace of the task space. So SPDL is simply not suited for a benchmark, and we are currently working on extending the benchmark to better compare SPDL. So we saw the comparison on skill specific. So we saw each of the advantages and drawbacks of each methods. So now we see the results on the parcours and the global performance experiments. So we simply compare the methods on 48 seeds with the 3 embodiments, no expert knowledge at all. So you can see all the methods on our chart. What we show here is the average percentage of tasks on which our deep reinforcement learning students obtain more than 230 of reward, which is what we considered as a task mastered. And you see the standard error of each curve. Okay, so what we can observe here first is that, again, expert knowledge 3 methods perform best simply because we couldn't provide any expert knowledge to methods here. And as we saw before, expert knowledge methods, ICR methods that use expert knowledge are very dependent on it. So they simply perform very poorly here. There's just an exception for Golgan, which is in blue again, and which at the beginning of the training is among the methods requiring expert knowledge, but then reaches kind of the same results as the methods without expert knowledge. So yeah, Golgan performs quite well without any expert knowledge here. Then we can see ADR, which is in green, which performs actually significantly worse than random. The reason for this is that we did not provide any expert knowledge. So ADR needs an initial task distribution to start from with simple task, and we could not provide it here. So it may have started somewhere very hard in the task space, and we have a very rugged difficulty landscape on the parkour. So ADR is simply stuck. Finally, so we have in the curves the results averaged over the 48 seeds, so with 16 seeds of each embodiment. But if we look at each embodiment and the results we obtain, we can see that none of the methods obtain good results on the climber. Again, we have a case study for this in the appendices where we show that while learning climbing locomotion is quite hard, but we show in our paper an experiment where we did it with a random teacher, so with our baseline, which obtains a very poor result here. We managed to get a very nice policy and nice result in a simplified version of our parkour. So we simplified the task space and reduced its size, and random managed to perform well. So what we show in the paper is that it's possible to learn climbing locomotion, but the current ACR methods do not manage to find the high learning progress niches to make the student learn. Okay, so finally, before concluding, as ACL in our case is made to obtain very robust and generalist policies, we obtain quite fun results that we wanted to show here at the end. So first, for the bipedal walker, we obtain policies that are able to go over hard obstacles like cliffs. With fishes, we had some of our policies and seeds that learned a quite realistic way of swimming. Same for climbing. Actually, we had some policies that were jumping from one creepers to another. And we did not use them in our experiments, but we also provide more realistic creepers. So our basic creepers are just fixed, but we also provide ones that can move. And so with them, we also obtain a very nice and realistic policies for climbing. Okay, as I've said, walkers cannot survive underwater, so when they are like kind of stuck in front of water, they fall in it and slowly drown. On the contrary, when you put a fish on the ground, it crawls as fast as possible to reach water. Yeah, we have similar behavior for chimps. So underwater, they start to drown, and yeah, at some point they die. And finally, we also played with the bipedal walker. We tried what we call the amphibious walker, which is just a version of the bipedal walker, which is allowed to go under and above water. And it actually learned a quite realistic and funny policy to swim. Okay, so to conclude this talk, we've introduced TeachMyAgent, which is a platform for systematic study of ACR methods. So it allows to compare state-of-the-art methods on key challenges of teaching, but also on a global performance assessment task, which is quite hard, as we saw. It also allows to simply add your own ACR method, and we release all the results. So you can simply download the results and train your own method and compare it against other methods without running everything again. So during this benchmark we made, we saw quite key results. First, that expert knowledge free methods perform very well, and that our parkour environment remains largely open. So this is quite nice for future methods. We are currently working on extending the current version. So of course we want to include new ACR methods, but we also would like to have new environments, especially with discrete or high dimensional task space. We also would like to have other tasks than locomotion problems. So we are, for instance, looking at ProcGen. And as I've said, for SPDL, we are looking for methods and problems where we do not want the ACR methods to try to make the student be generalist over the whole task space, but rather have a student which is very good in a subspace of the task space. So thank you for your attention. Here are the links to our GitHub with the release of TeachMyAgent that you can download, extend, modify. We also provide a website where we show all the results, and you can find our paper, which has been published at ICML 2021. And thank you again.